know alkenes have the general formula of, what is it, C. So if ethene is C2H4, then it's CnH2n, isn't it?
Yeah.
That's what an alkene is. But this doesn't take into account the actual structure. So I think this is an aromatic.
Yes.
Yeah, it's got a hexagonal structure. I don't think it's right to really call it an alkene. It's got alkene bonding, but I don't think it's functionally an alkene. That's not correct. It's functionally an alkene, but you know what? Never mind. I'm a physicist, not a chemist. Anyway, so alkene is cyclohexene is another industrial important alkene. That means it has, one or more carbon double bonds. Okay, so if we draw it, we get something like this. So it's a hexagonal structure. So cyclo, and it's got one double bond like that. Okay.
Yeah.
And we can imagine that at each of these other points, we've got hydrogen atoms.
Yeah.
So 1, 2, 3. So there's one hydrogen there, and there should be one hydrogen there. So that's 4 bonds per hydrogen. Cool. So it says, explain how the enthalpy change of hydrogenation of cyclohexene is used to give evidence for the bonding in the benzene molecule. Just so we know what benzene is. So this is cyclohexene. Cyclohexene. How do you spell that? Cyclohexene, yeah.
Like that, yeah. ENE.
Benzene, the true form of benzene is not what I'm about to draw right now. Yeah. The assumed form of benzene back then was actually 3 double bonds alternating. So cyclohexene triethene, I think it was called.
Yeah.
1,3,5 ethene. So it's basically this, but with 3 alternating double bonds. So one there, and one there. I'm not going to waste my time drawing all the. So this would be cyclohexene 1,3,5 triethene. I think my nomenclature of chemistry may be a bit rusty, but I think that's correct. Correct me if I'm wrong. Okay. So we're looking at this. Okay. We're not looking at what benzene is. We're assuming back then that if you're able to form 4 bonds and you're able to form like double bonds between carbon, theoretically, you should be able to form 2 more double bonds somewhere along the structure, right?
Yeah.
Now, the enthalpy change of hydrogenation. So hydrogenation is when you break open that double bond and you fill it with hydrogen. So it's basically an addition reaction. Hydrogenation is an addition reaction, right? And it's an exothermic reaction. So the first thing that I would write to begin my 3 marks is what the hydrogenation of cyclohexene is. And I would write something along the lines of hydrogenation is an exothermic reaction whereby, well, it's an exothermic addition reaction, sorry. It's an exothermic addition reaction whereby hydrogen is added to the cyclo molecule and the double bond is broken. The double bond is broken whilst new single bonds are formed. So I just want to stop there and focus on this idea of exothermic reaction. Why do you think exothermic reactions happen?
It's because energy is being released into the surroundings.
Why what factors affect what factors affect energy going in or being released out?
Bonds are being broken or made? Broken.
So you think bonds are being broken when in exothermic or no?
Yeah.
No.
Oh, it's bonds being made in exothermic.
Yeah. I'm going to explain this from a physical perspective because eventually we're gonna be taking a look at, I don't know, potentials, electric potentials, or I mean that's if you need to revise that, but
yeah,
like gravity and all that.
Mm-hmm.
When things get, so imagine two gravitational bodies, right? When they get closer together, or let's say we're getting closer to the sun, right? So the sun is a massive gravitational body. The closer we get to the sun, the more potential we lose.
Mm-hmm.
We lose potential. Basically, we radiate energy. The closer we get to the sun, the more stable we are. Because this goes back to this whole Big Bang theory and whatnot. At the beginning of time, what they call a priori, or whatever terms they want to use. I always thought that was a stupid term. It was really, really pretentious. I remember being in second year and my physics teacher would say, oh, a priori. Like, so I put my hand up. I was like, no, what the hell does that mean? And he's like, oh, at the beginning of time. Just say at the beginning of time then. Why are you trying to, anyway. So at the very beginning of time, we had this ball or this singularity of infinite matter, mass, energy, whatever, right? And it expanded outwards. Gravity's whole purpose is to bring everything back to unity, to bring everything back to that singularity. That's why gravity is perpetually attractive. It wants to bring everything back to a state of stability and really, really low potential. That's why when you look at gravitational potentials or electric potentials, it gets more and more negative. And that's just convention to show that you've radiated out all this energy. You've lost all this energy just to get that close. So when you're forming bonds, right, energy goes in. Sorry, when you're breaking bonds, energy goes in to break those stable bonds. Okay, you're breaking stability.
Oh, that makes sense. So they're being broken because energy is getting put into it, which means it's getting taken away from the surroundings, so it's endothermic.
Exactly. So let's actually write that down.
Okay.
Just as revision. So exothermic, energy goes in to break bonds. And then endothermic, sorry.
The other way around.
Okay, I can see where the confusion comes. So endothermic, energy enters, so the surroundings get colder. Energy goes in to break bonds. And then exothermic, energy is released because new bonds are formed or new stable bonds are formed. Energy is released because new stable bonds are formed. Okay, so in the hydrogenation of cyclohexene, what you're doing is that you're first of all breaking this double bond. So energy does go in, right? A fraction of energy does go in, but the assumption is that the two single bonds that are formed, right? You are going to get a hydrogen here and another hydrogen there, and then this double bond gets broken. The expectation is that the energy output from those two the energy output from those two single bonds being formed outweighs the energy taken in to break this double bond. Okay, yep. Let's actually check that. I actually want to check that. So bond enthalpy of a carbon double bond, and I just want to compare that. So what energy is, where's the carbon double bond? Carbon double bond enthalpy. Am I blind or is it not here?
I didn't see it.
This should be undisputed information. Like it's a carbon double bond.
615 at the top there.
Where did you see that? Here. Okay. All right. So carbon double bond is 615, but two CH bonds together. Look. So you're multiplying 413 by 2 because you're making 2 of them.
Yeah.
Right. So one carbon double bond is 615. Energy goes in to break that. Okay. But energy is formed when these are made. So imagine if we were to let's actually do that. So let's say, because actually the hydrogenation is minus 120 kilojoules per mole, right? This is a standard value. Mm-hmm. I think you would have to quote this in this question. You'd have to say that it takes, or it gives, the energy output, the enthalpy change is negative 120 kilojoules per mole. Mm-hmm. I think you would have to quote that. But let's see if we actually get that in calculation. So one carbon single bond gets broken and it's positive enthalpy change of 615 kilojoules per mole. Yeah?
Yeah.
But then 2 carbon single bonds are formed. So 2 times CH, and that's a negative enthalpy change of 413 times 2, 826 kilojoules per mole. And then when we do the math to find the difference, so 615 take away 826. Okay, I wasn't really expecting that. But it's probably not as clear cut as that. There's probably some other quantum mechanical things that make this not that value. Mm-hmm. But I know this enthalpy change is negative 120. It's in the books. I know that for a fact.
Yeah, I mean it's not far off. I guess there will be other factors that influence it.
Okay, so we write enthalpy change is negative 120 kilojoules per mole, right? So when these dudes were trying to predict cyclohexene 135 they would assume that hydrogenation happens 3 times, okay? Because there's a potential for hydrogenation here, here, and here. So effectively, you would multiply minus 120 by 3. So we would write benzene. The way this question is worded isn't very, very honest. It's not honest because we know that this isn't benzene. This question is actually asking you about the historical account of what they thought benzene was. That's the problem with this question. That's why I would expect a few people who are untested to get this wrong, because they're thinking, wait, I thought benzene was this ring. So what's going on here? Not knowing that this question is actually asking for a historical account. How does this predict, or how does this try to predict what benzene is? And this is what it predicted that benzene was. But this is not benzene. But, how does the enthalpy change predict benzene? Okay.
Right. Yeah.
So the enthalpy change normally is negative 120. Benzene was thought to have 3 double bonds. So enthalpy change was theorized to be negative 360 kilojoules per mole. Okay. And I think that's around 3 marks.
Yeah, that makes sense.
Because me being the guy I am, I would be tempted to start waffling about, but benzene isn't really that because this, that. I think that's for the next question. The next question is a what? I think it's a 6 marker. Yeah, it's a 6 marker.
Yeah.
So I think all of that information is for the next question.
Yeah.
Okay, so any questions on this?
No, I get that. I think I knew the theory behind that. I just struggled to put it into words.
Okay. So let's have a look at the next question, which is a massive 6 marker. And remember, like when we're given these long ass questions with 5 to 8 marks, the general strategy is to give a point and then to attach scientific evidence to that point. Okay, so that's 2 marks. Point, scientific evidence. Point, scientific evidence. Point, scientific evidence. So really, we should be comparing, or we should be making about 3 to 4 points to get these 4 marks. Okay. All right. So let's write again cyclohexene. So let me just copy and paste this and delete these because we're not hydrogenizing them or hydrogenating them. So that's cyclohexene. And then benzene is this ring thing. Okay, before we actually answer the question, let's make a distinction of what this ring means. So this ring, from what I've recollected, the p orbitals of carbon, they overlap. So you know how carbon, you know how every atom has like orbitals. You have the s orbitals, you have the sp, d orbitals and whatnot, right?
Yep.
Carbon has 6 electrons in its outer, does it? No, it doesn't. No, carbon has 6 electrons in total.
Yeah.
2 in the inner shell and 4 in the outer shell. So that's 1s2, 2s2, and 2p2, right? The p orbitals overlap. So every single carbon atom here has its p orbital overlapping, and that basically creates a chain or well, I wanted to say train because it keeps going round and round. Like a train or a ring of delocalized electrons that form that stable structure. Okay, so the ring represents a chain of delocalized electrons that were created from the overlap of 6 carbon p orbitals. And they all lie in the same plane. I think benzene is a flat structure. I don't think it has a 3D shape. I think, but let's see if Google proves me wrong. Is benzene flat? Yeah, benzene is a flat molecule. Yeah. So the p orbitals all lie in the same plane. Okay, so it's a flat structure. Okay, and this ring is what gives benzene an amazing amount of stability. That is why when we expect 3 times minus 120 to be the hydrogenation of benzene, that's addition, which can't really happen anyway. But let's say if benzene could undergo addition, which it can't unless you break the ring. Let's say benzene could undergo addition. It's not going to be negative 360. It's going to be less than that. Why? Because, what was my reasoning? I had it in my head. Because the ring structure is so stable. The ring structure is already so stable. The difference between breaking this and forming new ones is small. You know, I need to make sure I have that very convincingly. Energy is released because new stable bonds are formed. So the amount of exothermic energy is the difference between the bonds that you formed. So if you have this, which is really stable, so let's say that this is more stable than this carbon thing, and like you're making addition. So let's say that this was to make this. Sorry, my logic isn't really logicking. I'm trying to justify the fact that this is really stable. So if you make new bonds, the difference between the enthalpies is smaller. The difference between the enthalpies is smaller. So
Right.
so here we had like 2 times 413, which gives you 826, right? So the enthalpy change would be a measure of the stability between this bond and these 2 bonds, right? And that will tell you about the stability of the bonds. However, if the difference in enthalpy change is a lot smaller, then that gives information that this is really stable. There's not much you can do to make it more stable. That's what I'm trying to say.
Yeah. Okay. Yeah. It's like as stable as it can be.
Exactly. Yeah.
Yeah.
Okay. Oh, I probably should have said that. There's not much to make this more stable than it already is. So the enthalpy change, well, the absolute value of enthalpy change is a lot smaller. Okay, so let's actually compare these two. So the first thing that I would write is that cyclohexane does undergo addition. Why? Because it doesn't have a delocalized ring. Its functional group, so we should use key terms here. Cyclohexene has the alkane functional group, which accommodates addition. What type of addition? Electrophilic addition. So we're using key terms here, and that's how we're ramping up our mark. We're using key terms here. We're using functional group because, you know, in chemistry, we have the carboxylic acid functional group. We have the ketone, the C double bond O oxygen functional group. I think that's a functional group. We have if it could be called a functional group, the CH functional group. We have the C double bond functional group. Each of these undergo slightly different reactions depending on what they're reacting with. The alkene functional group accommodates electrophilic addition. Now we need to explain what electrophilic addition is within the context of bromine, right? So basically, bromine water. You would dump cyclohexene into bromine water. Bromine water containing Br molecules, right? That's what bromine is, yeah?
Yeah.
Dissolved bromine in aqueous solution. When bromine approaches a C double bond, like in cyclohexene, it gets an induced dipole. Because this is an area of extremely dense negative charge. So dense negative charge, okay? So this entire double bond is really negative. So when the bromine gets in close proximity with this area of dense negative charge, you get an induced dipole. So this changes to a slightly positive polarity, and that changes to a slightly negative polarity. Okay. Now, because of this induced dipole, this isn't going to change. Okay. This negative charge density isn't going to change, but that is going to be attracted to that negative charge density. So what you get is that you get the addition of this electrophile. This is essentially the electrophile.
And it's an electrophile because it's positive and it's attracted to electrons, right?
An electrophile is anything that is electron deficient and would gladly accept an electron pair.
Okay.
So electrophile, as it is electron, because the electrons have been pushed over. The electrons have been pushed over to the negative Br. So this is an electrophile as it is electron deficient, and is happy to accept an electron pair, of which is provided by this carbon double bond.
Mm-hmm.
So let me move that over to this side. And then you get an intermediate, state whereby this breaks off. And so you've got a negative radical bromine. You've got a negative bromine, what? This is, in my opinion, that's a radical, right? A radical is anything with a lone pair, isn't it?
Yeah.
So you've got a bromine radical, and then on the other side, you've got this Br and this carbon, which is now slightly positive because the electron pair has been taken by the Br here. So now this is electron deficient. This part of the carbon is now electron deficient. So this is the intermediate state. But all that does is mean that this Br radical can attach to that deficient area to create the full addition of Br onto the onto this thing here. So you end up getting, so that disappears, and then you get two Brs right there. So this would be called cyclodibutane. I don't know what's called, but it's got two butanes in it. I mean, sorry, not butane. It's got two bromines in it. So I was
cyclodibromohexane.
Yeah. Yes. Wow. Okay. You know what? That's actually a logical name. So
cyclodibromohexane.
Dibromohexane.
I think.
Okay, let's just put quotations on that.
Yeah.
All right. Definitely search that up, because don't write that in an exam if it's wrong. Yeah. Okay, so we've explained why this happens, and then you get your marks for basically narrowing this down into a couple of sentences, right? So I'm gonna write here process as illustrated. Process as illustrated, but described. So make sure you describe it. Okay, so something about you need to write induced dipole. You really do need to write induced dipole. So induced dipole. Electrophilic addition. Probably need to mention something about the bromine radical. And yeah, okay?
Yeah.
Right, so, one more thing. Cyclohexane decolor, because of this process, when you pour cyclohexane into bromine water, it decolorizes bromine water. So because of this, cyclohexane decolorizes bromine water. Okay, bromine water is like brown in color. Yep. And because of this electrophilic addition, it decolorizes bromine water. So basically it becomes colorless. The bromines stop being dissolved in solution, and they start bonding to, so basically it's like they disappear from solution. Okay, how is this different with benzene? My question to you is, do you think benzene can undergo addition? And if it, why not?
Because of the dense ring of delocalized electrons in the middle of it.
Yeah, you would have to break that ring in order for it to undergo addition.
Yeah.
And 9 times out of 10, you either don't want to do that or you don't have the ability to do that. So the first thing that we would write, benzene cannot undergo electrophilic substitution due to the stability of the delocalized ring. It can, however, within certain circumstances, and I'm not too sure if you should write this. I think it's worth writing because it shows a level of chemistry that, you know, is beyond simply giving examination style answers. Basically, if you use UV radiation to basically break the ring, you can start adding bromine onto it, and then you'll end up with bromine on every second bond. So sorry, that doesn't make sense. You'll end up with bromine on every second vertex or whatever that means.
Right. Yeah.
But you need to use UV. If you want addition, you need to use UV to break the delocalized ring. Otherwise, you are left with substitution. So benzene instead undergoes substitution with the aid of a catalyst, And I think a catalyst is like, is it aluminum bromide or iron bromide?
Yeah, ALBR.
ALBR, okay. And what happens is that, this is ALBR2 or something like that, because aluminum can form, anyway. So the result of this is that the carbon atoms here, sorry, the hydrogen atoms here, they simply get swapped with bromine. So bromine comes in, kicks off the hydrogen, and the hydrogen then runs away with the other pair, with the other bromine part of that pair. So when you dissolve aluminium bromide in solution, I think you form, or I guess you form, it's as if you've got like a bromine pair. One of that pair becomes electrophilic. So I think this is electrophilic substitution.
Mm-hmm.
One of those bromines of the pair, again, does this whole shebang here. Yeah. But rather than being added to a double bond, it just kicks out a hydrogen. So this hydrogen becomes an electrophile as well, because it's now electron deficient. And that hydrogen bonds to the nucleophile or the radical to form HBr. And the electrophile bromine replaces the hydrogen there. Okay, so let me illustrate that in a picture. So we got this. So that's, you know, really dense negative charge. So very negative. So we've got our bromine. That's slightly negative and that's slightly positive. And that, I'm not going to draw the whole thing. That becomes Br and then plus HBr here. Yeah. So electrophilic substitution. I think it's called electrophilic substitution. Electrophilic I don't want to be making words up. Electrophilic, all terms up, substitution. Spell it properly. Electro happens in containing benzene rings. Okay, yeah. So that is electrophilic substitution. Okay. So again, this is pretty straightforward to put into words. A thing that you have to compare is that benzene cannot decolorize bromine water.
Yeah.
So because of what we set up here, benzene can't decolorize bromine water. You need to write that down.
Yeah.
In the if this question came up. So benzene cannot decolorize bromine water.